So I want to start by giving a big thank you to Victoria, who reminded me I forgot to keep posting videos. So this will be the last video for 6.4. We'll do an example when we get into class, and then we have a worksheet with examples from 6.2, 6.3, and 6.4 in class on Tuesday. So we're now going to formally state what the steps are to testing hypotheses. So doing a hypothesis test for a single proportion. So we're going to put a framework on what we sort of went through in a very casual way with that coin example. So the first step in hypothesis testing is to set up your hypotheses. So instead of having these sort of competing statements, which are essentially the underlying piece like we did in the helper-hinder example with maybe they just got really lucky and it was just due to chance, or perhaps there is some reason that the babies chose the helper toy. Instead of having that, we're going to use this a little more mathily. We're going to say our null hypothesis, like we talked about way up at the beginning of 6.4, is that our true proportion is equal to some value. And you can call that the null value or our initial value, whatever you want. You can put a P naught there, but I'm just going to say this is what our first piece is. H naught is P is equal to something. So in our previous example, that something was 50%. Just like in the helper-hinder example, we assumed there was nothing going on, it was a fair coin, or we assumed that the babies were just choosing at random, so it was a 1 in 2 chance. The other side to this is that we also need an alternative, right? This is what we're going to basically assume from the get-go and sort of work towards, but we want to have an alternative that we can say, well, if this isn't true, this must be the option. So 3 different possible alternatives: our right tail, our left tail, and our two-tailed alternatives that we saw back at the beginning. So do we care about, like we did in the helper-hinder or the coin flip example, do we care that we want to show that it's greater than 50%? There's some reason the babies are having a choice for choosing the helper, or that our coin is giving out more than 50% heads. But we could also be saying we want to show it's giving out less than 50% tails. So we could have used this as well for our alternative if our success was tails instead of heads. And then the last example, I don't care what the actual value is. I just want to show it's not a fair coin, or that there's something going on. The babies are choosing in some direction. So these are our 3 options for our alternative hypothesis. So essentially identifying examples, and I just answered this like I said I would in the last video on accident. So this is a fair coin in terms of words. That was our null, and our alternative was we had some proportion that was more than 50% heads, and our roommate was a cheater. So there's 2 pieces to setting up these null and alternative hypotheses. If you want to kind of think of this as steps, step 1 is going to be to figure out what the heck our null value is. Is it 50%? Are we just saying half and half like our 2 examples we've done so far? And then number 2 is the direction of my alternative hypothesis. If you can get those 2 steps down, you're golden for setting up your hypotheses. So here's where I'd like you to take a moment, pause the video, and try out the examples in exercise 6.4.2. See if you could identify what the hypotheses are going to be. So in 6.4.2, I'm going to start with the first one here. We can see in 2003, there was an accident rate of 12%. They've given us some potential proportion, right? It is supposedly the true proportion for 2003. As we keep reading, we are interested in whether the true proportion of young drivers having accidents has increased since 2003. So we're saying, okay, obviously we're not in 2003. So we have 2 options here. Oops, that should be a null. Either the proportion now in 2017 is the same, this should be colon, sorry, is the same as it was in 2013. We always need to have our equals in the null hypothesis. In fact, the first thing you can write down is all of this, because that's never ever going to change. And then we can just say, okay, the rate we're interested in testing is 12%. And then our alternative, now is when you look for a keyword. We're still talking about P, our true proportion. We're still talking about 12%. We're just adding a direction or an inequality to this equals that was on the null hypothesis. And this is where you see, oh, increased. We're doing what we call a right-tailed test. So if you didn't pause before, I'm going to highly recommend you do now, because the next two examples are a little more challenging, and that'll make sure that you understand, now that you've seen it in action, can you do it yourself? Okay, so example 2, or B, I guess. We can see one survey showed that among 785 randomly selected subjects, 18.3% smoke. Now this is in the same sentence as a sample size, so this is likely a p-hat. Test the claim that the rate of smoking among those with 4 years of college is less than 27% rate for the general population. So now they have given us another P. This is why we spend so much time reading for p-hat versus P in 6.1, is because the same thing's going to happen here in 6.4. We're going to have 2 different percentages given in some questions, and we have to identify, in this case, which one is from the sample and which one is the one that I'm going to test or is my claim. So they're telling us this is actually a real P from the population. We want to see if it's the same, or if the value for college grads, or people who've done 4 years of college, is less than that. So we've got our 2 pieces to this. Our null is going to be about P equaling 0.27. The proportion for college, students who've done 4 years of college, is the same as the general population. Our alternative, also about P, also about 0.27, and then we're going to bring in our directional keyword of less than. This 18.3%, this is our evidence. Is 18.3% less than 27? Indeed. That's what's going to let us know whether or not we have actually, we have evidence for what we want to prove, because usually we want to prove something like this. Okay. Our last one here, we know where it's going to start. We're just going to have H naught is P is equal to something. HA, our alternative, is going to be P and that same something. In this particular example, in 2002, we see 7% of hospitalizations were for affective disorders. And then we have a sample taken this year of 1,000 hospitalizations, shows that 80 were for affective disorders. We wanted to translate everything we were given here. We had a true value from 2002. We had a sample from this year with a number of people who fit that criteria from this year. So if we wanted to, we could go find a p-hat. But that's not our goal here. Our goal is to figure out what our null and alternative are. In this case, we do want our value from 2002, because we want to say, has it changed since 2002? And then we're looking at an alternative of not equal to, because our keyword here is just changed, which means I don't care if it's more, I don't care if it's less, I just want to show it's different than it was back in 2002. All right, so that's step 1. Can you set up these hypotheses? And if you tried this on your own, you should be really good to go. If you set these up incorrectly, your whole hypothesis test is going to fall apart. So this is that one step I always tell students when we're working on something in class. Try this step at least on your own. Step 2 is we just calculate a z-score. Essentially, that's what we're going to do. We're going to go and look at our mean for a p-hat is real P, but we don't have real P, so we use our P naught. Our standard deviation for p-hat is equal to the square root of PQ divided by N, but we don't have P, so we're going to use our hypothesized value. We're going to do exactly what we did in the last example with the flipping of the coin. So we're basically just taking our observed value minus the mean we expected, dividing by the standard deviation. So this is a z-score as we are used to. It does have a different name. We call it a test statistic in this framework because we're not using the true mean and the true standard deviation. We're using a guess at the mean and a guess at the standard deviation. So it has a different name and we call it a test statistic. But since we have made a z-score before, and I believe all of you can plug into that formula, I don't have any examples that make us actually work through this. And we get to move on to step 3. In step 3, we find what we call a p-value. Now, p-value, what it actually means, I'm going to jump straight to here and then we can talk about what that crap above is. It's the probability that we got out what we got out. So in our coin flipping example, that we got 60% heads if it's really a fair coin. If the real mean is at 0.5. So that's the big piece to this. It is technically a conditional probability. What's the probability my p-hat is as crazy as my p-hat is if Real P is what we say real P is. So that's what our p-value is all about. It's a probability. And if we have a z-score, finding that probability is pretty dang straightforward. So let's, oh, and then we got some other pieces here about our p-value. The smaller our p-value is, that means it was very unlikely that what we got was what we expected. It was very rare, and therefore we have more evidence that we're not in that null hypothesis scenario. We're not in chance world, as we saw. So we're going to put that together with step 4 and some examples. So step 4 says, okay, once you find this probability, you can then make a statistical decision. So if our p-value is less than alpha, and alpha is some set value we call a significance level, it will always be given to you. I do think I have a couple of homework questions where I didn't give you an alpha, and in that case, the most common is 0.05. And that's what you'll use on those questions where I did not give you an alpha. But on a test, I'll make sure to give you one. If your p-value is less than that, that's our threshold for something being very rare, essentially. So if it's less than that, then we're going to reject the null. We're going to say, okay, remember our example before, fair coin versus giving more heads, right? Cheating. Since we had, in the second example, when we did it with 200 flips, we came up with a value that was lower than every single one of these rejections, the significance levels. We would reject this saying, well, this is so rare, I don't think that this is actually the case. Chances are it's much more likely that we actually have a roommate cheating or that we have a coin that's unfair. Now, here's a big piece to this. Sure enough, it makes sense that we reject this value if it's incredibly unlikely that is basically kind of true. But the other piece to this is, in the case where we had only 20 coin flips and we got a like 18% possibility that that would happen, that we would get 12 out of 20, we never get to reject this. That never happens. What we just say is that we failed to reject this. I still don't believe it. Right? It's not my goal as a statistician is to disprove this and prove that this is what's happening. But I never get to say disprove this side because it's not what I worked with. I worked with this side. I don't get to prove that it's right. I just say that I failed to reject it. So we're going to go ahead and see what this looks like in an example. So in this exercise, we're going to go ahead and find p-values for a number of different test statistics. So they plugged into that formula that we've had before and done that piece for us. So the first one here says this is a left-tailed test. So a left-tailed test is when our alternative is that p is less than some value. And what this means is that when we get out our z-score, in this case negative 2.46, we are interested in a left tail. Less than is, well, shade the less than side. And we want to find this based on our z-score. We could obviously use normal CDF with our mean of 0 and our standard deviation of 1. But this is one of those times that I actually think that the z-table is way quicker than using normal CDF if we already have z-scores. I'm going to use the z-table that we saw on the last exam to show you this. So the left side is exactly what our z-tables do, what our normal table does. So we need to look up negative 2.46. So that's all we're going to do. Look up negative 2.46. That's going to give us the area to the left of that, which is our p-value. So let me zoom in a little bit. Negative 2.46. Looks like our p-value or our probability is 0.0069. That's easy. And to me, that's easier than using normal CDF. Now, if you like normal CDF, you could definitely use that here. So that's step 3, finding our p-value. Now we're going to see what step 4 looks like. Basically, this is the probability we would get out something that unusual. Is it more unusual than our suggested significance level here of 0.01? Yes, this is smaller than 0.01, meaning that it is very rare. And in that case, we would reject the null hypothesis. If you want a cute way to remember whether you reject the null hypothesis, I got a little piece here for you. If the p-value is low, you reject the hoe. Obviously, hoe here refers to null hypothesis. So if you had any other ideas in mind, I'm not sure where you got those. So anyways, what I also like to do whenever I reject the null, you can't really see it because I did a bad job of circling, I love to put an exclamation mark next to it because this is what we want to do as statisticians. We're hoping to reject the null. This is when we get to say that we have results that are statistically significant. We can say, oh, look, my roommate's a cheater, or there's some reason that babies are choosing the helper toy. We're hoping for this. So if we do those last two examples, if we do a right tail test, same business here, we have 1.67, and now we are caring about the right tail. In terms of our alternative hypothesis, this one would have had a p with a greater than. This would have been what we were doing and was what we were doing in the example with the trash can and the coin flips. And if we want to find our p-value, we have lots of options. We could look this up and subtract from 1. I personally like just looking up the negative z-scores. Whatever the heck my z-score is, I know my p-value is a tail. You see that word tail? So it has to be something less than 50%. So there's no point when I go to my table here to look up something on this bottom half where all the percents are bigger than 50. This is where tails are, right? Less than 50%. So if I want to look up 1.67, I'm not even going to bother with the positive half of the table. I'm going to look up negative 1.67 instead. That's going to give me the same value if I had looked on the opposite side of the graph. So 0.0475 is our value, here. So 0.0475. And again, if we do our comparison piece, this is less than that alpha of 0.05, barely, which means we again get to reject the null and say, indeed, something is going on. We have statistical significance. So our last example is a two-tailed test. This is a little bit different. This is where things get funky. So we have our z-score here, a negative 1.33, which is not a terribly unusual z-score. Also, if I wrote down my alternative hypothesis here, it would be p is not equal to some value. In a two-tailed test, I don't care if my value is below what we expected or is above what we expected. So we actually really want to do both of these tails. Now, our steps are going to seem similar to before. I'm not going to look up two different things. I'm just going to look up, as I said before, the negative z-score. Because again, there's that word tail. I want a tail. So negative 1.33. So I come back here. Negative 1.33. Choop, choop, 0.0918. I keep wanting to make that small and I can't. 0.0918. Now I did not write that down as my p-value because it's not. We are doing a two-tailed test, which means I just found this. But I also cared about the above, right? So I need to actually take this and multiply it by 2 and get 0.1936. And you can see here, if I forgot to multiply by 2, I'd actually make the wrong decision. Because now that this has been multiplied by 2, this is greater than our alpha level, greater than our significance level, which means for the first time, we're going to do the sad thing and fail to reject the null. This is when we get to say, yeah, I'm afraid I couldn't reject the fact that, you know, this could be a fair coin. Doesn't mean I think it's a fair coin, but I don't have the evidence to prove what I wanted. So there's one final step to do this problem, and that is to state your conclusions in the context of the problem. So this is how it goes. We start with reject the null is whenever we get to say there is the evidence to conclude. If we fail to reject the null, we just say there is not the evidence to conclude. This statement, regardless of whether we reject or fail to reject, will end in the same way. We're going to put in HA in words. We're never going to talk about the fair coin example. We're never going to say, hey, yeah, blah, 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 anything about a fair coin. We're just going to say, there wasn't the evidence to prove that the coin wasn't fair or that the coin was giving out more heads. Never say the coin is fair. We'll never mention our null hypothesis, our initial assumption. This is actually when the whole idea of guilty versus innocent is a little bit more useful, because when we say in a court case, we assume at the beginning everybody's innocent, right? That's our null hypothesis. It's our starting point, innocence. What we're trying to do, especially as us as the prosecutor, is prove that they're guilty. At the end of the trial, what we say is that there wasn't the evidence to prove the person was guilty. You don't get declared innocent at the end of a trial, right? You just get declared that there wasn't enough evidence to put you away. So we have one final example I'm going to do here. I'll save the last exercise for class. But you and your roommate have a special coin. Again, if you want to show that it gives out a larger proportion of heads, if you designed an experiment, you took all that time, you flipped the coin 200 times, and you got 90 heads instead, would you still want to set up a hypothesis test? Why or why not? So in this case, we want to prove that our proportion is greater than 50, same as it was before. But our p hat, our x over n, we only got out 45%. This is not going to make sense for a hypothesis test. A hypothesis test measures how much evidence we have based on our p hat. We don't even have evidence for what we want to prove, right? Here's what we want to prove. We want to prove it's greater than 0.5. This is not evidence. This is actually evidence that we've been getting away with not taking out the trash as much as that we might, think we are. So what we would do with this question is we would just say, oh, never did that experiment, just going to toss those results under the rug. I'm never going to mention it to anybody. And that's actually something that is a very important thing in science, is this idea that we only ever report out when we have statistically significant findings. And we don't report out when things don't work out. So for all you know, if you get your statistically significant findings on your study, someone could have done a similar study and gotten non-significant ones. And you don't know which of you is right, because no one ever publishes that. So you don't even know how many people have done such studies. So this is a big deal within science, is this, if it doesn't work out, we just toss it away. If we also wanted to set up this as a sort of hypothesis test, since we're looking at a greater than, we would shade the right hands, and you'll notice we're not even getting a tail here. So big problems all around, but it wouldn't make sense. And this is why it is possible to sort of use that cheat of always looking up the negative, because you wouldn't even set up this hypothesis test. It would never make sense to go ahead and keep going when you had something that wasn't evidence. So like I said, I'll save this last exercise for class. And with that, you're done with your videos for the week.